Okay, to round out circular motion and to round out two-dimensional motion, I kind of want to start with this problem because it's a good problem to segue into what we're dealing with in the next chapter. So far, we've been talking about kinematics without regard to what's causing the motion. So what's giving it that push or that pull for the motion, and that's what we're about to start getting into. So what I've got here is I've got a car that's traveling in a flat circle of radius r, and at a certain instant we're told that the car has a velocity of 24 meters per second west, and the acceleration can be described as having 2.4 meters per second squared east and 1.8 meters per second squared south. Now, first of all, we're going to look at the west being a negative and the east being positive, and we want to find out what the radius of the circle is. So the first question we might ask ourselves is, why did the author of this problem suggest that it was a flat circle? And this is our segue into the next chapter. We need to care that it's a flat circle because if I'm on a banked turn, those are those turns in when you take a turn off of the interstate or you take a turn on a hill, you'll notice that a lot of them are banked, and there's a reason for that. That helps control the acceleration that we experience, and there is a practical reason that we build in those banked turns. You look at a NASCAR track, we got banked turns. And that also brings me to the fact that there in your Blackboard, there's a folder called Cool Videos on Circular Motion, because I want to kind of introduce those here because we've been talking about circular motion as part of our two-dimensional motion. So I also provided a link to the hyperphysics that really goes into looking at these banked turns. But for right now, because we're still in two-dimensional motion and we haven't quite changed over to that next step, I just want to show you what the situation is here. We have a banked turn, and we can describe that banked turn as what we call an inclined plane. You're going to find out that physicists love inclined planes. We just love working problems with inclined planes because that helps us describe what's happening in the world. And like a banked turn, it's a really good practicality. So if we've got our car, and I've represented that car as a box, on that banked turn, we know that there's an acceleration due to gravity, and we're going to find out that there's a force due to gravity. So we're going to make that step next. But we already know we have a center-seeking force, or that centripetal acceleration, because you've already looked at that lecture. So we have that part. So we have an x and y component to that centripetal acceleration because of the banked turn. And that's why we have to know that in this particular problem, we are on a flat circle. We're not on a banked turn because that would complicate this problem even more so than it already is. So as with any problem, the first thing we want to do is draw your picture. So at this point, I've got a circle here. I've got the velocity going west. I have a y component of my acceleration. I have an x component of my acceleration, and I have an r. And we're trying to find the radius of the circle, so we want to find that magnitude of r. And so we want to do that. Now, when we are dealing with circular motion, remember, we're talking about how things are moving around that circle. And we've already introduced the idea that I have an angular frequency. Remember, period is going to be the time to make a complete cycle. My angular frequency will be how many cycles in a second, or in a unit of time. So my angle is going to be a function of time, and we're going to call that omega t, which you already saw in the lecture video. And I really want you to go back and look at your text. Look at the examples 4.3 and 4.4, because that's really going to go into how we're going to go from our motion vector to our velocity vector to our acceleration vector, and you can actually see how those things are working. So we've got our r, and our r is going to be how those x and y components go. So my r is going to be r cosine omega t. My y is going to be r sine omega t. And we know that the velocity is that first derivative, and that's where this negative sign comes from. So even though you guys haven't seen this yet in your calculus stuff, but your derivatives of sine and cosine, the derivative of sine is going to be cosine. The derivative of cosine is going to be minus the sine. So we can get a value for our velocity, and we can get a value for our acceleration. And in my general physics class that we don't use calculus at all, we just give them the equations, okay? For you guys, I want you to see where they come from, but for right now, just knowing that that's how they come about really, really works. And when you get into your calculus class and you see where that derivative comes from, you guys are going to be just peachy dandy fine. So that's how we're going to be there. So let's write out our vectors, okay? So we're going to write out our vector components. So I want to kind of go through this, and I'm doing this real quick just to remind you of a trigonomic identity that we need to use, and we'll use it several times, is that the sine squared plus cosine squared is going to equal to 1. And so that if I have my vector r, I can show that the magnitude of that vector is r, given how I've written it out. Now, when you look at it in terms of the example 4.4 and 4.3, you're going to see that they're going to use A to represent our R, or A to represent amplitude, because that becomes really how important it is with my circle, because my unit circle, A would be 1, and then A would be 2, 3, 4, 5, and 6. Think about going around in the merry-go-round again. If I'm on the horse on the inside, I'm at a smaller circumference than I would be on the other side, but all the horses are going to make it around the merry-go-round at the same time. And I've got to deal with that different amplitude. And we'll see that again. So I'm going to write these coming from the problem, right? Coming from the problem, we're told that the magnitude of the velocity was 24 meters per second. My amplitude, or not my amplitude, but acceleration was 2.4 in the I direction and a negative 1.8 in the J direction. Both of these are coming from the problem, right? Both of those were information that was given in my problem so that I can write it out. So now, one of the things that we know about circular motion, and that's where kind of the logic comes into this problem, because you might take a different approach to it. So when we're talking about those problem rethinks or those problem reflections, I kind of want you to do a problem rethink and a problem reflection on this problem. So I'm going to make that assignment. I want you to do a problem rethink and a problem reflection on this, because if you just look at this and we know, kind of put your piece of paper over this if you're going to print this form out. Put your paper over it. But if we know this question and I know this, what are some of the rabbit holes you might go down? And that's really what I want you to do on that problem rethink and reflection. I want to know what kind of rabbit holes that you might go down on this. Because I sat here and worked it, and I went off on a rabbit hole, and I went, oh, God, I'm being silly. I went off on another rabbit hole, and I went, oh, God, being silly. And the other part I want to think about is this right here. Does this logically make sense? Well, if I'm traveling just around on my unit circle, no. But if I'm traveling along a path where I can take each little arc segment of my circle to define my path, that acceleration could really be there. You know, that acceleration could really be there, because look at how this acceleration is. My velocity is going this way, but my acceleration is going backwards. I'm being pushed, according to this, if I'm sitting in my car, I'm going to feel like I'm being pushed into the seat. So I want to look at that really closely and kind of think through it. So, but we know that for circular motion, that our acceleration is center seeking, and that's by centripetal acceleration. And in section 4.6, as well as in the lecture, we show that the centripetal acceleration is equal to that velocity squared, and this time we're talking the magnitude of the velocity squared, and divided by the radius of the circle. But here for our system, my centripetal acceleration at the instant when I'm at that 24 meters per second going into the west is going to be my AY. And this is really the whole trick of this particular problem. I got to look at that AY. And so when I do that, then I come in and I plug that in. I solve for R, and I find out that it's 320 meters. Or the problem may want it in kilometers, so I may have to convert it to kilometers, so it's 0.32 kilometers. And then if I'm talking about a highway embankment curve, I am talking about something that I might want to represent in kilometers more so than meters. The other thing I wanted to kind of point out, because I haven't really done it really well in any of the lecture material so far, is that I can get that angle for my vector just for my vector components. So I can find the magnitude of my acceleration. So let's go ahead and do that, because I'm going to take my 2.4 squared, my 1 plus my 1.8 squared, and I can show that the magnitude of that acceleration is 3 meters per second squared. I can also determine the angle by using the tangent. And that's going to be my y over my x. And think about your unit circle diagram again, that right triangle. I can calculate that angle. And now if I do the arc angle, I'm going to show that it's a negative 36.9 degrees. And here's where a big caution comes in. So when you're doing your homework and you're doing a variety of things, you really need to know where that angle is coming from. And so if I'm drawing my two vectors for my car, here's my velocity vector as my 24 meters per second. Here's my acceleration vector, which has a magnitude of 3, and that negative 36.9 degrees tells me that I'm in this angle. And you're going to find that a couple of times because we're going to figure out those angles, but it may not necessarily be in the quadrant that you're talking about or the way that WebAssign wants you to see it. So hopefully this really helps. I encourage you to do this. I want you to do the problem rethink and reflection on this problem in and of itself. And that will be in the Blackboard section of our assignments. And I hope this works. Bye.